Welcome to this video course on blueprint reading for welders. This session serves as a comprehensive introduction to interpreting technical drawings for welding applications. In this first unit, we will cover the basics of blueprint reading and sketching, specifically focusing on the essential lines and views used in technical drawings. Lines are the primary communication tool in any blueprint. You must learn to recognize each type of line and understand the specific purpose it serves. Every line has a specific weight and style. Object lines are thick and solid, used to show the part's visible outline, while hidden lines are broken and of medium thickness, showing features not directly visible. Establishing scale and location is key. Center lines show the center of circles or arcs. Extension lines define dimensioning points, and leaders point to specific surfaces for notes. Fabrication often requires looking beneath the surface. Cutting plane lines indicate where a cross-section is taken, while section lines define the material surface exposed by that cut. Different materials have unique patterns or fingerprints in section views. These lines are typically drawn at a 45-degree angle to help identify the material type. We also use special case lines. A phantom line indicates alternate positions or relationships to other parts, while a chain line shows the specific location and extent of a surface area. Break lines are used to conserve space on a drawing. A heavy, freehand, irregular line signifies a short break, while a light zigzag line indicates a long break in a part. Understanding perspective is crucial. While isometric drawings help with visualization, orthographic projection is the standard for describing objects with the precision required for fabrication. Orthographic projection follows strict rules of alignment. Views are placed in a specific arrangement to ensure the front, top, and side perspectives remain properly aligned with each other. When selecting your front view, the anchor view strategy suggests choosing the profile that is most descriptive, regardless of its physical position on the actual object. Imagine the object inside a glass box. When you unfold the sides of that box flat, you reveal how the different views relate to one another in position. How many views are enough? There is no strict limit. Use as many as necessary for clarity, though 3 properly selected views are usually sufficient for most fabrication tasks. To summarize, object lines define shape, section lines identify material, orthographic projection provides precision, and the front view is selected for detail. Accurate reading of these elements is essential for error-free fabrication. Welcome to Unit 2. In this section, we move from interpreting blueprints to creating your own. We'll explore technical sketching as a tool to bridge the gap between mental concepts and final blueprints, transitioning from 2D views to 3D visualization. Sketches are essential when time is tight. Master the line technique by avoiding continuous sweeps. Use short, overlapping strokes to build lines, keeping them light until the shape is defined, then round your pencil point to darken final lines. For arcs and curves, accuracy comes from structure, not guessing. Build a frame first. Use a right angle with equidistant guide points or a triangle layout to anchor your curves and maintain geometric control. Advanced geometry requires specific methods. Use grid layouts to establish intersection points for concave and convex arcs. For ellipses, remember they represent a 2D circle viewed at an angle. Use a centered triangle to establish the major and minor axes. Oblique sketching uses a frontal approach. Start with a true shape orthographic view for your most complex face, then use 45-degree parallel projection for receding lines. Foreshorten the depth by half to ensure the drawing appears realistic. When constructing an oblique form, follow a logical workflow. Start by drawing the front face, then add the receding axes. Connecting these points forms the complete 3D volume based on your initial front face layout. When dealing with oblique circles, use the cube method. By sketching the circle within an oblique projected square or cube, you can maintain the correct proportions and alignment of the curve within the skewed perspective. Isometric sketching uses a different standard, typically defined by 30-degree angles. This method provides a clear, balanced view of all 3 primary planes, making it highly effective for visualizing complex parts before detailed drafting. The box method is your best tool for isometric sketching. Do not draw lines in empty space. Instead, construct a bounding box that represents the overall dimensions of the object, then sculpt the details within that established volume. In isometric views, circles do not look like circles. They appear as ellipses on all 3 primary planes. Understanding this distortion is key to accurately representing cylindrical features in your 3D sketches. To construct an isometric circle, use the four-center method. Start by drawing the isometric rhombus, lay out your construction lines to locate the four centers, and then draw the elliptical arcs step by step for a professional finish. Developing cylinders and curved forms requires layering. By combining the isometric box method with circle construction, you can accurately represent curved surfaces, holes, and cylindrical protrusions in your technical sketches. How do you choose between oblique and isometric? Oblique is superior when the front face contains the most complex contours. Choose isometric when you need to clearly display multiple faces of a part with equal visual importance. Keep your best practices in mind. Maintain line hierarchy, use grid paper for angle discipline, and always prioritize visual proportion over exact dimensions. If your sketch looks wrong, re-verify your bounding box. We have now covered the essentials of sketching. In the next unit, we will move beyond lines to decode the notes and specifications found on technical drawings, which are critical for any welder to understand. Welcome to Unit 3. In this segment, we address the information gap, the critical details that exist beyond the lines of a drawing. Understanding these notes is essential for accurate fabrication and professional welding. Local notes provide specific instructions for a particular feature. These are placed near the relevant part and use a thin leader line to indicate exactly where the requirement, such as a specific weld type, applies. General notes are the universal rules of the document. These apply to the entire part or assembly, rather than one specific location, and are typically grouped together to ensure they aren't missed. Specifications serve as the project's recipe. When a note defines materials, welding processes, electrode sizes, or rod types, it provides the technical requirements that ensure the final product meets engineering standards. Deconstructing a specification link requires careful attention to detail. Every reference standard or material callout acts as a mandatory instruction that must be followed for structural integrity. The title block is the document's identity. It provides the foundational information needed to identify the print, understand its origin, and verify its status within the design process. Title block analysis begins with identification. This area contains the drawing number, part name, and company information, ensuring you are working with the correct and most current document. Technical data within the title block provides the mechanical requirements for the part, including tolerances, scale, and projection methods, all of which are vital for meeting precision standards. Administration and history sections of the title block tell the story of the document. These fields track revisions, approval dates, and engineering changes, maintaining accountability throughout the project lifecycle. Finally, we consider the drawing sheet itself. Standard sheet sizes follow established formats that allow for efficient printing, filing, and handling, ensuring consistency across the entire set of technical documents.